Welcome to this short recorded lecture on homeomorphisms. So this is an application of continuity. So this still is within the section 2 of the Pew book in chapter 2 on metric spaces. So the idea is that a bijection, a continuous bijection that also has a continuous inverse is a homeomorphism. And this effectively means that you can think of M and N as fairly equivalent. That is, there is an equivalence relationship between them. Now, the basic idea in some sense is like this. The letter Y and the letter T, even though they look different, you can imagine if you took the letter Y and you took the letter T, that if you took here I'll have to use a different pen to give you kind of the sense of this. I'll use red. If you took those parts and bent them down, there's a continuous transformation. Here it's like the process of this. You can start moving them down very continuously in those directions until you get to this T. And that at the same time, if you have the T, you could take these parts and start moving them up, grab the ends, like if it was made out of rubber, and then you could build it back towards the Y. So this would be like the F, and this would be like the F inverse. And so somehow the points that are on the spaces Y and T are similar to each other. So there's your homeomorphic. There's actually, if you go to YouTube and look up a lot of videos involving homeomorphic transformations between objects, you can see why like a coffee mug is homeomorphic to like a donut. They're pretty interesting to see and to think about. And so he goes into this very deeply, actually, in this text. We don't go into it too deeply, but just enough so that you can see it as a nice application of continuous functions. I like the geometrically speaking part, that a homeomorphism is a bijection that can bend, twist, stretch, and wrinkle a space to make it coincide with another space. But it cannot rip. It cannot rip, puncture, shred, or pulverize the space in the process. And so it's useful to think, what are the spaces that are homeomorphic to each other? And what are the continuous functions that you can consider from between two homeomorphic spaces, or to show that two spaces are homeomorphic? So he goes into a lot of details and some abstract things involving this throughout, and there's some interesting problems. But we're just going to, we're going to dabble with it a little bit. So the one that we really care about, the reason that I'm interested in presenting this in some sense at all, other than it is conceptually interesting, but I think for our purposes, I really like to get towards isometries. So an isometry is a distance preserving function. But more than that, he's defining an isometry as a bijection that preserves distance in the sense that for every point P and Q and M, that when you map those points to N, then f of P and f of Q, which are points in N, have the same distance as P and Q had in M. So that's what it means to be distance preserving. So then two spaces are said to be isometric if there's an isometry between them. And isometric metric spaces are indistinguishable as metric spaces. So every isometry is also homeomorphism. It's continuous, these results. You should try to prove this. It's fairly straightforward. You really just exploit this, and the proofs are fairly short. So I want students to try to do that. But one thing you can say is if there's an isometry between two spaces, two metric spaces, then kind of a mouthful of a thing to say is they are isometrically isomorphic, or meaning they are isometric and homeomorphic to each other. So usually we'll just say isometric, though, for short. So we said equivalence relation. You have to kind of think like, okay, prove that an isometry is an equivalence relation. If M is isometric to N, show that N is isometric to M, right? Show that each space is isometric to itself, that if M is isometric to N and N is isometric to P, then M is isometric to P. So if you read that and you kind of go like, that just sounds like a lot of words. What did all that mean? Well, let's look at what an equivalence relation is. An equivalence relation is just some binary relation that has the properties of being reflexive, symmetric, and transitive, which is similar to what we've seen with a metric space itself. A metric is something that has a non-negative positive property. The part of that might be considered reflexive. A is equivalent to A. And symmetric is very similar to what we've seen. If A is equivalent to B, then B should be equivalent to A. They're just using equal here for that. But usually we're going to use like a notation like a tilde for equivalence, not this equal. This is just from, I think I grabbed this from Wikipedia, I think. And then there's a transitive property, which is kind of like a triangle inequality. If A is equivalent to B and B is equivalent to C, then A is equivalent to C. So again, those are supposed to be tildes, and it's just kind of sloppy right there. So I get some idea about how you should go about doing this here involving isometries, but I fill in details involving this because this is really getting towards why I like isometries, is they give a nice way to describe how to complete any metric space. But before we even worry about that, we're going to set some foundational results for us that prove quite useful later on in understanding what I'm going to say. So if X is a metric space, imagine that you considered any two Cauchy sequences in that metric space. Now a sequence is Cauchy looks very much, the definition of Cauchy looks very much like convergence, except you don't concern yourself with a limit, because there are spaces where Cauchy sequences don't converge. You can always show that a convergent sequence is Cauchy, but a Cauchy sequence doesn't necessarily converge. You have to be in a space that is complete for Cauchy and convergence to be equivalent concepts. So that being said, I give this definition here about a sequence being Cauchy, and then I say in this problem here, prove that this right here defines an equivalence relationship between Cauchy sequences. So the proof of this is to say, well, look, I'll consider three Cauchy sequences, that are contained in that space, made up of points in that space. And then I need to check if this property, this one right here, has a reflexive, a symmetric, and a transitive property. Because if it does, then it defines an equivalence relationship. So then I can say, even if I have two Cauchy sequences that look different, if this property holds, I can consider them equivalent. So the reflexive property is pretty straightforward. The distance between Pn and Pn is always 0, which means a constant sequence converges to 0. The constant sequence 0 converges to 0, which means a Cauchy sequence is equivalent to itself. No big surprise there. What about symmetric? Well, the key is to use the symmetry property of metrics to say that the distance from Pn to Qn is the same as the distance from Qn to Pn, which means that if Pn is the Cauchy sequence Pn is equivalent to the Cauchy sequence Qn, then Qn is equivalent to the Cauchy sequence Pn. Again, not so surprising, and you're just using the symmetry result to prove from a metric to prove the symmetry property for an equivalence relationship. And then the transitive property. I exploit the triangle inequality from a metric to prove this. If Pn is equivalent to Qn and Qn is equivalent to Rn, my goal is to show that Pn is equivalent to Rn. So I need to show that that converges to 0, the distance from Pn to Rn. And I just use the triangle inequality to show that. And then I'm using the fact that this goes to 0 and this goes to 0. So the sum of two sequences of real numbers that converge is the limit of the sums, is the sum of the limits, and the sum of the limits in this case is 0 plus 0. So there you go. So I should actually really say that this is by elementary analysis, right? That's really how I got to there. So there you go. This does define an equivalence relationship. So you can consider two very different Cauchy sequences, but if this is true, that the term-by-term distance between them goes to 0, those are in some sense equivalent Cauchy sequences, even though they might be different at every term. So then there's this problem that I ask you to do, which is to say, well, let X tilde be the set of all equivalence classes so obtained. So you're looking at the space X now, and you're thinking of it not in terms of individual points, but in terms of all the Cauchy sequences you could possibly construct from it. And then you're saying, all right, this is now a space not made up of points, but of equivalence classes. So this point P and this point Q in X tilde contain all the Cauchy sequences that are equivalent to each other. So then you're asked to show that if you define a space made up in such a way, then you can actually construct a metric on it. So this is a capital delta here, and you're basically saying delta of PQ given by this limit as n goes to infinity of the distance between Pn and Qn, that is a valid way to define a metric on this space of equivalence classes. That's going to seem really strange. That might take you a while. That we're going to work on that in class. One of the things that you might try to tackle before class is this lemma. If Pn and Qn are Cauchy, then the sequence of real numbers defined by their term-by-term distance has to converge. And that has to converge regardless of whether or not these Cauchy sequences converge, regardless of whether or not this is a space that's complete, meaning that Cauchy sequences converge. So this always converges. What you do is you exploit that the reals are complete. You exploit a result from elementary analysis that says convergent sequences are equivalent to Cauchy sequences. So if these are just two arbitrary Cauchy sequences in a metric space, what you should show is this right here defines a Cauchy sequence of real numbers, which means it converges. Then you have to show, after that, that if you interchange Pn and Qn with any other 2 points from these equivalence classes, so any other 2 Cauchy sequences that were equivalent to them, then the limit that you got here, the limit of that new sequence of real numbers would not change. So you'd have to figure out how to show that. Those are necessary things that you have to prove first in order to show that this operation, defined this way, is actually defining a metric. So I'll write it out like this, that delta is defined on x tilde cross x tilde into 0 to infinity. That this defines a metric on x tilde. Okay? So it's going to seem really abstract and strange, but we're going to work with some examples. You're going to get used to doing this a little bit. You're going to have to struggle with it a bit. And then when you do, you get to a result like this. And I've highlighted a few things here, and I just want to walk through it. For every point in a metric space, there is a Cauchy sequence, all of whose terms are p. And what I wrote here, what that means is I'm saying consider the constant sequence that's just that point over and over again. That constant sequence converges. It's trivial to show that, well, it's straightforward at least, that to show that a convergent sequence is Cauchy. So to every point, you can consider that there is a Cauchy sequence that at least converges to that point. We're not saying every Cauchy sequence converges, but there's at least a Cauchy sequence that's constructed by every point in the space X. Okay? So then you're saying let capital P sub P be the element of equivalence classes within that's a single point within X tilde which contains that sequence. Because maybe there's other Cauchy sequences that are equivalent to the constant sequence of all P's. So as an example of this, consider the fact that the sequence in the reals, like this would be the sequence that is a Cauchy sequence containing the point 0, which is a constant sequence 0, and that's equivalent to this sequence of reals, even though they're different. So this is one point in this equivalence class, and this would be another point in this equivalence class if the point P was 0. So you stop considering in X tilde individual points as opposed to Cauchy sequences. And all the Cauchy sequences that are equivalent to each other make up a single point in this space of equivalence classes. Again, it will take a little while to get used to that. But if you hear it now and you start working with it before class, that will help. So then there's this operation that's described here. I'm going to just switch pins real quick. Excuse me. There we go. You prove that this metric you've defined between capital P sub little p and capital P sub little q, given by the distance between P and Q, is equal to that. So what you're proving is that this mapping phi of P to capital P sub little p defines an isometry of X, and this is important here, into X tilde, not necessarily onto. So it's isometric to the image, right? So this would say that phi of X is isometric to X. Okay? And this, I point out here, this is a big whoa statement. This is actually really cool. So what this basically means is that every point in the space X defines a point in X tilde. But X tilde, because this is into, may be bigger, think more complete, I keep saying complete here, than the original space X. And this is going to have some profound implications in terms of our ability to complete any metric space. Because ideally, like a really desirable property of a metric space is completeness, that Cauchy sequences converge. Unfortunately, there's lots of metric spaces where Cauchy sequences don't converge. And then you can run into a lot of issues using those spaces in practice. This is laying the groundwork for us to be able to describe how to complete any metric space by reconceptualizing the points in the space not as a single fixed point, but as a single Cauchy sequence that's equivalent to possibly all sorts of other Cauchy sequences. And if you, in that other Cauchy sequences in that space, I should say. And when you take this different perspective, this allows you to view a complete version of that metric space. As an example of this, and like I said, this is going to be hard to grapple with. It's going to take some time. If x is the rationals, then x tilde is isometric to the reals. So this is giving us a way to go from the rational numbers to the reals, to fill in all the gaps on the real number line that are left by the rational numbers. We're not going to necessarily get into that and all the details here, but I'm laying the groundwork here, and this involves continuity and mapping and convergence of sequences and defining things are metrics. So this is a nice problem at the end of week 3 to really tie together kind of every single thing you've seen so far in this class. So that's why I put this problem here, and it also lays the groundwork for something involving completeness that we talk about later. So it's just one of those problems that I picked apart parts of it so that it is possible for us to solve these things here, but it is going to be conceptually a complex problem to deal with. So this will take up the majority of our time dealing with this and dealing with examples of this in class. So thanks for listening, and I'll see you in the next lecture.